Hello. In this video, I will be covering the basics of coding in Verilog and relating this to RTL design. If you haven't already, I would suggest watching video parts 1 and 2 for a full explanation for how to use Vivado to run and simulate Verilog code. Firstly, it is important to understand the very basics of hardware design, which is based upon the idea of logic gates. Logic gates are input-output modules that give a certain output based upon what logical operation is taking place. The most basic of these operations are the AND, OR, and NOT gates. These gates are used to transport data in the most fundamental aspect that a computer can, using ones and zeros. Using these logic gates, 0 represents absence and 1 represents presence. This can also be thought of 0 being represented as false and 1 being represented as true. As you can see on screen, here is the symbolic representation of each gate, which can be found when looking at a digital circuit diagram. Associated with each gate is what is known as a truth table, which is a way to visualize what the output will be of each gate depending on the combination of input values used. For the AND gate, it will only output 1 if and only if both input values are 1, as seen in the truth table. For the OR gate, it will only output a 1 if the input contains at least one 1 value. For the NOT gate, it simply takes the inverse of the input, so 0 becomes a 1 and vice versa. These logic gates are the most basic aspect of digital circuitry and can be combined in various ways to have your circuit reflect the behavior you want to capture. A very basic example of this could be an alarm system circuit behavior that can be simplified with logic gates. Let's say, for example, you want to turn on the alarm if the doors are locked and the alarm system is turned on and the pressure sensor detects something or the glass breaks. This can be captured with the following logic. Before writing any Verilog code, I would suggest reviewing these concepts until you feel comfortable using them conceptually. The next concept to understand before writing any Verilog code is the idea of clock signals and data paths. This is very important to understand in RTL design and Verilog, so make sure you are comfortable with this before writing Verilog code, as this is essentially what your Verilog code is supposed to represent. A clock signal is essential for digital circuit design, as it is essentially the timing of your circuit. Most data path elements that store bits, such as a register that holds these bits, would have a built-in clock signal that would store data on the rising clock edge. There are numerous examples of data path elements that can be combined to express more complex circuit behavior, so make sure you review what types of data path elements you would need to express your desired digital circuit. Some other examples of data path elements are adders, comparators, and counters. A data path element is simply a module that performs an action on bits based upon what input it is given. As mentioned previously, a register is a module that stores a certain number of bits. Another example of this would be a multiplexer, commonly referred to as a mux. It is a very simple module that has a control input to allow a certain input signal to pass through. As you can see by the image, the control input of the mux is a binary number that corresponds to what input gets passed. 00 corresponds to the first input, 01 to the second, and so on. Note that the number of bits needed for the control signal depends on the number of inputs used. In this example, a 4x1 mux is used, which requires 2 bits for the control signal. The length of the control signal can be calculated as 2 to the x bits needed for n number of inputs, due to each digital place needed in binary to represent each input. Now, I will cover some basics of Verilog coding by describing some example code. The following is an example of some basic Verilog code that exemplifies the usage of logic gates as mentioned previously in this video. If you are familiar with C code, the syntax of this language is very similar to C and was created to emulate the C programming language. Firstly, note the declaration at the top stating the time scale. This is an important header needed for Verilog code, as it gives a reference to how long delays are to be interpreted for the simulator to run. The 1 nanosecond per 1 picosecond means that delays are interpreted in nanoseconds and fractions are rounded to the nearest picosecond. Next, notice how modules are defined in Verilog syntax. They can be thought of as being equivalent to functions in C programming, except contained within the curly bracket here, where both the input and output names are listed. The end module at the end of the code can be thought of as the closing curly bracket of a function in C programming, as this is interpreted in Verilog to be the end of the module. The naming conventions for modules, inputs, and outputs follow the conventions in C programming. Case sensitivity matters and will not be treated the same. Notice that the keyword reg is important for declaring the output of the module, as this is necessary when using always blocks, which appears below. The keyword reg represents a data storage element in Verilog whose value is retained until it is updated. The always block, whose syntax is shown in Verilog, describes events that should take place under certain circumstances. Notice the usage of begin and end, which serve to define the region of the always block and function similar to the curly brackets in C code. Certain constraints can be used to specify when the always block should run, but in this case the always block will run due to the specification of always using parameters A, B, and C. But, for example, an always block could be specified using the phrase pause edge clock for a variable named clock, which could represent the clock signal used in a circuit. This would only run during the pause edge of the clock, which occurs when the clock turns from 0 to 1. The two outputs of this module, F1 and F0, are assigned with values depending on the logic gates used. In Verilog, the syntax for logic gates are as followed. Tilde is not, ampersand is and a vertical dash is or. The following image is what the logic gates for F0 and F1 would look like. This can then be tested using a testbench file. The testbench file will contain a combination of input values, in this case for A, B, and C, to test if the output values are as they should be expected. For this example code, the testbench would look like. This code appears similar to the code shown previously, but contains a few differences. Notice how the declaration of inputs and outputs aren't necessarily in the module header. Instead of using the input keyword, use reg in the testbench, and instead of the output keyword, use wire. In the next statement, these dummy test variables will be mapped to what appears in the original Verilog code in the .v file. Then, using an initial block, which also requires usage of begin and end keywords, a combination of test variables can be used for the input. The usage of #10 signifies the timing of each variable assignment, so each assignment occurs within 10 milliseconds of each other. So the first assignment will occur, then 10 milliseconds later the next one, and etc. This is where the timescale keyword at the beginning of your code is important, as #10 would correspond to 10 nanoseconds if the timescale was 1 nanosecond. The 1b notation indicates the binary value which is being assigned and how long the binary number is. The first number is the bit length, and b indicates the binary values are being used, followed by the value of either 0 or 1. After writing a testbench file, by running a behavioral simulation, a timing waveform diagram can be generated to see if the values map correctly to the output as expected for this logic gate. This is a very basic example of how Verilog can be used to describe digital circuitry combined with the simulation power of Vivado. Further practice and learning is necessary to gain a strong understanding of Vivado and Verilog. Thank you for watching, and I hope you found this video informative.